Good evening, everyone, and welcome once again. This is the Monday night third week of the technician class. Well, I know they call it technician class license class to make it easier for us. Tonight, we're going to delve into the world of electronics and radio electronics. Before we begin, before I go to the book, I want to explain some things that will make learning this a little easier. To begin with, when electricity was first discovered by mankind, had no idea what it was or how it worked. In fact, it goes back so far because of things like lightning, static electricity, and other phenomena that the ancients named gods to be in charge of things like thunder and lightning. So, like just about every ancient religion around the world, the ancient Greeks had Zeus throwing thunderbolts. The Norse religion had Thor with a mighty hammer pounding out lightning and thunder. The Native Americans in North America and in South America, they all had gods attached to the phenomena of electricity and lightning. And in fact, so much so that the Native Americans in North America, who didn't actually have gods, they had spirits. They had a spirit called Thunderbird. And Thunderbird was the horse with wings that charioted in the lightning and static electricity and all that. Well, around the 1700s, they started to experiment with electricity. And along the way, they couldn't have been farther from what would eventually be our current understanding than you could get. First of all, they didn't conceive of the idea that electricity might be a negative charged particle traveling in a wire. They thought, well, maybe it was a positive charged particle traveling in a wire. And of course, that's why some electricity is backwards on the way we refer it. We refer to two things in electrical flow. We say the flow of electrons travel from negative to positive. A positive spot in electricity is a spot where there is a missing amount of electrons to be a balance in the world. A negative spot is where there is an excess of electrons. It's a little confusing because electrons have a negative charge themselves. And while we define this as a negative charge now, it all goes back to the fact that we once had it backwards. So to fix it, we just said, okay, we'll fix this. We'll make electrons negative and protons in the atom will make those positive. Now, it works out real well for physics. Sometimes it gets a little confusing in electronics. We're going to try to get through some of that. By the way, I never thought to mention this in the other time I taught the class. The very name of Tom's organization, how do you guys pronounce that, Tom?
Anemoi incident response.
Yeah, Anemoi is a terrible British mispronunciation of the Greek gods that controlled the weather. The Greek word anemoi, it refers to the Greek gods that controlled the weather and the winds and thunder and lightning. There was a whole host of them. And by the way, the British are real good at mispronouncing anything they encounter in another language. And one of the things they like to do is most of the languages of Europe, other than English, the I-shaped character is really an E-shaped sound. So that's why we pronounce countries like Iran and Iraq improperly. Their real names are Iran and Iraq. And of course, that's thank you to the British translators who translated it to English. So the same thing happened here, except that in the case of anemoi, in Greek, the OI sound, OI character sound, the O is silent. It's always an E sound, not an I. So it wouldn't be an anemoi, it'd be an anemie. So it doesn't quite sound as nice, I don't think. So we'll just move on. So we're going to go and I'm going to share out the book. And here we are at chapter 3. Now, before I go to chapter 3, I'm going to go back one page, I think. No, I'm not. It's not here. All right, we'll move on. Chapter 3 starts with electricity. In this chapter, we're going to cover the foundations of electricity, voltage and current, resistance, capacitive and inductance, reactance, impedance, and resistance, and common electrical components, and then basic radio circuits. This is a lot. This chapter will be the only one I chop into all of this week and part of next week because there's a lot to cover here. I want you to have enough of a basic understanding that you can answer all the questions quite simply. Now, as we move ahead in the book, I'm going to skip by the questions for now because we'll get to them. Okay, and I don't want to jump this far. I wanted to show you basic electricity, which is here. Come on. Very uncooperative. There we go. This chart on page 3 on or figure 3.2 is handy to conceptualize. It's not necessarily correct. The primary elements of electricity in an electrical circuit is there's some source of electrical stored energy or generated energy, a power source, either a battery or a generator or power from the grid, whatever. And electrons flow, and the flow of electrons is defined as current. Now, in order to have current flow, you have to have some potential difference. The potential difference is the difference between how many electrons are missing here and how many electrons are extra here. It provides the push to make electrons flow. But if you notice from this, the arrows here are backwards. Electrons are actually flowing the opposite way of these arrows. So what I referred to earlier. The flow of this is where from positive to negative is called conventional electron theory or flow. It is an imaginary flow that current itself flows from positive to negative, but the electrons go from wherever the most negative is to the most positive in the real world. But I'm going to stop this and I'm going to go to a drawing real quick. I'm going to do a drawing with you. So I will stop this share and we're going to go to a real quick little drawing I'm going to draw for you right on the spot. And why did my drawing programs go away? All right, I'll keep talking. Well, that chart that I showed you, and we're going to go back to it, will help make this all the comparison to fluid pressure or to water pressure is what I'm going to what you want to use that chart for. But we're going to do a little understanding of how electricity works. Okay, I'm hoping you all can see this drawing screen. Somebody give me a thumbs up. Excellent. All right, so we're going to draw into this page. I'm going to take an eraser out and take out this dot I didn't put there. And I'm going to make a couple of kind of cool lines like this. And I'm going to make another one of those cool lines. I'll move it down here. And now I'm going to go to the text here, and I'm going to start typing in much smaller characters. A couple of a bunch of E's and a bunch of O's. I'm going to make this side I'm going to make this side our minus side, and this side our, oh, come on, plus side. There we go. Now, if we had some, if we had a large plate, well, maybe I should have put the O's on the opposite side of them, but this will work fine enough for concept. If we had a large plate, and on one side of the plate we had all the electrons lined up, it would be a negative value there, or a negative charge there. And on the other side, if there was an absence of electrons in the outer shells of the molecules of the material, that would be a spot where the electrons, that would be a positive charge area, which means it's a spot where it would like to acquire electrons. If they were equal, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7, 8, which I didn't do right, but it doesn't matter, then all these electrons would balance out. In this case, all these 9 electrons can't go here because there's only space for 8. Doesn't matter right this minute. It won't matter in basic electricity. It's just a good concept to understand. They can't go where they can't go where there isn't a potential difference, a difference of the charge potential, and that is voltage. If they all moved over here and canceled all the rest of these out and it became neutral, in fact, I'll tell you what I'm going to do. I'm going to change this a little bit. I'm going to take an eraser for your benefit. I'm going to erase out these. And I'm going to put that text back in here and make the wrong letters. Okay. And I'm going to move all this right here. So now let's imagine 2 different plates. One has a positive charge on the plate, one has a negative charge on the plate. Imagine that they go all the way across, but I put them on each end just because I did. Now, if we get the electrons to go from here to here, we have to have a means of getting there. And what that would require would be an electrical circuit. We'd have to have a wire going from here. Oh, crap. Try this again. Trying not to just jump right here, but we have to have a wire that goes like from here to here. Now all these electrons can go across here and counter those out by coming across and through here. But if we did that, it's just a dead short. It would heat up this wire, probably burn it out. So a handy thing would be not to do that, but to put something in the middle. One thing we could put in the middle would be a light bulb. Now, as the electrons flowed through here, they'd heat up the light bulb and they'd go across and they'd come over to here. And the light bulb would light up, which would be really pretty cool. And that's basically how a basic electrical circuit works. This light bulb would glow, hopefully yellow, because it's a yellow light bulb. But hey, I picked the wrong color. All right. Not too far. In fact, one of the first diagrams I'll teach you is that basically a battery, the symbol for a battery, well, those should be straight lines, is like this for that reason, or pretty close to it. And the battery, they shorten every other line for the positive, negative, positive, negative. And the reason they do that is because by doing it shorter, longer, it indicates that one has excess electrons, one has an missing element electrons. Now, when the two drawings, when you have a symbol like this, let me make straighter lines. But when you have a symbol like this, that's that's straight in electronics. That's a symbol for a capacitor. A basic capacitor is physically what this line looks like. It is a one plate separated from another plate. There's usually insulation material in between. And the way that a capacitor works is when you charge up one side with electrons, it pushes electrons away from the other side. So you get a positive and negative charged side. And then if you come out here and bring a wire around, the electrons will discharge. And of course, if, as I drew before, you put a light bulb in between, it would light that light bulb, not for long, but it would, because it would rapidly discharge. And in fact, early flash systems, electronic and flash bulb systems both, utilize capacitor discharge systems, as do modern day automobile spark plug systems and a number of other devices, one of which is called a taser. Don't touch them. At least don't touch the part that discharges them. We'll find out in this class basically how that works. Now, when electrons are flowing through a wire, this is the part that gets a little murky until somebody explains it. If we got this wire flowing here, These electrons they don't flow straight across the wire. Because if they did, it would take a long time to get from one end to another. In fact, when electrons move, they don't move very far at all. I can't draw this effectively, but I'm using a shaky, fuzzy line on purpose because these electrons don't move any further than the next electron to them. When they move, what there's atoms in between. What they're doing is they're shoving one electron to jump to the next one, to jump to the next one, to jump to the next one, and so on. They're jumping across the atoms in the conductor. The difference between a conductor and a non-conductor, which is an insulator, is that a conductor has electrons or electron holes, if you will. It has spots where it will either take um, or send, easily accept or easily give off an electron. In the case of good, better conductors, it does both. It will both release and accept electrons to let them move. So think of them as vibrating next to each other, and their motion is making whatever motion started here ends up here. Now, the stuff I'm teaching you right now is to help you to grasp the concepts of how things work and not necessarily what you need in detail. You don't need in detail to understand that the drawing of the atom that I showed you with the fuzzy electron orbits around it, or the more orbital design, which is called the Bohr's model of an atom. Those are concepts to help chemists and physicists and so on understand what's going on. It helps us a little bit. But what we need to know about it all is that a conductor is a material which readily allows the flow of electrons, or more realistically, the flow of electrical current. Electrons don't actually go from one end of the circuit around to the other. They don't go from the positive or negative terminal to the positive terminal. That one electron doesn't travel all the way around. It moves a little and moves the next one a little bit, and sort of like playing bumper pool all the way around. Or not bumper pool, but Dodge bumper cars. One bumps another. It's a chain reaction type of thing. And they bump themselves across. So conductors are the materials which have in their outer electron orbits or energy levels, they have they have incomplete shells or orbital locations. So they have room for electrons to move. So their outer shells or orbits, the word that chemists and physicists use for their orbits is shells, because they're not circular, like I said. Well, they're not full. Simply put, the further from full they are, the better uh, uh, conductor they are, because they've got more spaces for electrons to move. The opposite side of that is insulators. Insulators don't like to move electrons around because their outer orbital shells are already full. There's nowhere to move. There's no lee room. There's no empty little space to move one and then another and then move another type of thing around. It's sort of like the chiclet like game that you probably all remember, a little drawing type game where you slid a little chiclet sized uh, plastic piece around and you could move one and then you could move another one and then you could move another. If you only move with one space at a time. Well, if that was full, you couldn't move any spaces at all. And if it had fewer little chiclet type tiles in there, you could move a lot easier. But, and that is a good explanation. Now I'm going to go back to the book. We're going to go back to the drawing. Share screen. And where did it go? Here it is. And we're back on this drawing. So now I've defined for you that electrons get nudged all the way through in a circuit. When they're in motion, that is current. Conventional theory says that current travels the opposite way of the electrons. We only define this that way because of some physics that you will never have to worry about. And it really doesn't matter which way they go. It really doesn't. All we need to know is that the electrons flow by nudging each other and they all balance out. And when they balance out, this battery is dead. Because all the electrons from here will now have balanced out zero over here in the battery. Now, we can measure the voltage because it's sort of like the pressure that's pushing the electrons around. The battery voltage is the unit of measure, but the actual name for it is electromagnetic force. It's a force. The reason we call electromagnetic force is because anytime electrons move at right angles to them, they create a magnetic field. That is super, super important to remember. So we refer to it as the potential difference, but it is a force, an electromagnetic force, and it has a unit measurement of volts. Just like pressure is what pushes a gas or a liquid through a pipe, it is the potential difference or electromagnetic force that pushes electrons around. In reality, it doesn't really push, it draws. But that doesn't matter. It's all the same thing. Again, it's only tomato versus tomato when you say push or pull. Now, at the same time, if pressure is flowing, if air is flowing, if it's flowing through a pipe, you have flow. Flow is not the same as pressure. Flow is actually in motion, moving around. Pressure exists whether there's flow or no flow. Same is true of electromagnetic force. There's voltage present whether there's a flow or no flow. So you measure voltage from across what we refer to as across the line, from one side of the source to the other side of the source. But to measure current, you have to measure through what it's flowing through. And that's where this drawing is a little deceptive. You really need something in here like a light bulb. If you measured through the light bulb, and now I'm going to unshare this, I'm going to share you a circuit drawing that I drew. I'm hoping it shows up. Here it is. All right. I'm hoping you all can see this drawing. And I was hoping it wouldn't be off center like that. There we go. This happens to be an AC signal source, but it doesn't matter. We're going to use this drawing for a lot of things. It's going to make things explainable. But if you imagine this was a battery instead and just disregard these waveforms here, well, then if we measured um, from here across here, and this was a battery, the measurement between the two, this would be the voltage. But to measure the current, we would have to actually interrupt this, and we'd have to take our measurement through a metering device. I guess I can just draw anything as a, yeah, I guess I can just draw a box in there. Let's put a 2D shape in a box in there. So if we had a meter put in between here, and the meter had a window with a nice little dial in it, why, this is how we would measure. This is how we would measure current. So that meter would go across here. We would not have to break the circuit to measure the voltage. To understand why is because the voltage is pressure. It's not dependent on the flow of electrons. It's a force, it's a push. Okay. The current, which is measured in amps, is a flow. And the flow of electricity is a motion. It has to be measured in the path of the motion. In this case, you got to kind of stand in front of the race car and let it run you over to see if it's moving. And that's why we don't put our fingers in the middle of it to check for a current flow. We don't want to get run over by the great electrical race car. It kind of tickles you something fierce. Now, in the circuit, in the class, we're going to talk about there's a couple of types of electrical circuits. The two fundamental types that we'll concern ourselves with. I'm jumping ahead here. This is a series circuit. This one has a parallel circuit. They're very different. And when we get to that point, what I've just said to you is going to be very important. Because remember, a series circuit, all of its elements are in the flow of each other. So they share the same current. A parallel circuit, they're not in the flow of each other, and they share the same voltage. And we'll go into how we calculate that and learn from it and so on. But I'm going to jump back to the book right now. Okay. You know, this is probably one of those times when I probably should have opened up my whole screen. Have I got the book up, guys? Good. All right, we're going to move forward. So use this to help you remember pressure or push or force and flow. So you can grasp the difference between flow and current, which is the same, and voltage and force or push. Now, there's one more component of electricity that's very important, and that is resistance. We commonly refer to it as the load. The load is whatever is doing work with the electricity we're pushing through the circuit. If it's pure resistive, that means that the flow is going through a device which is turning it into heat 100%. Easiest thing to understand that does this is an electric range or an electric stove. The heating element, it's real easy to see. Electricity travels through, it gets hot. A light bulb does this. Electricity travels through, it gets hot, but it also makes light, which is another form of heat energy. And a radio does this because it takes electricity, and we end up making radio wave, which radiates out. And that process of it radiating out or becoming heat or being used is called work. And work is measured, work is what it sounds like. You're getting something done with the electricity. Work is measured in units of watts, and we define it as power. And there are relationships between the three. Oh, they have drawings like mine. Fancy that. I'll come back to this. And the relationships between the three, you have a nifty little drawing in your book. Actually, 4 elements that relate to each other. The voltage of a circuit, of any electrical circuit, is going to be the current, is going to equal the current in amps times the value of resistance in ohms. It's defined. It's the definition we use for calculating electrical circuits. And it works 100% if you keep the units proper. And we're going to cover units in a minute. But the power of a circuit, and that's where we're going to start, how much work a circuit can do, is based upon the flow of the electrons and how much is pushing it through that flow will determine how much work it can do. And in electricity, we measure power. The unit of measure is watts, named after James Watts. The unit of current measurement is amperes, named after the Frenchman, I forgot his first name, Pierre Ampere. And the unit of measure of the push or the electromagnetic force is volts. Now we have these 2 little nifty charts, 2 little circles in the book. When I get to these in the future, I'm going to show you how to use these without having to do any math. But they all not only explain the relationship, but you can use them to do your math calculations simply by substituting the numbers into the spot. Anyways, we'll go through that when we get there. I don't want to jump too far ahead all at once. All right, I'm going to stop this share. No, I'm not. I wanted to stay there. Darn it. Read share. I want to back up in your book is what I want to do. All right. Go back to where we were. Come on. All right. So actually, this drawing is the drawing that I had drawn in the other of my own. I forgot it was in the book. This one's a battery. And I think I'll go through a little bit of this right now. I've already covered the fact that this one is a series circuit. This one is a parallel circuit. If one of these light bulbs goes out, it opens up the circuit. You all remember the old light Christmas tree lights. When one went bad, you had to go change them one at a time to find out which one of the darn things. That's why we don't wire houses like this. The other thing that you have to understand, each one of these is dropping the voltage. So the total voltage from here to here to here, it could be different on each bulb. You could have, if you had different valued bulbs, like a 20 watt, a 15 watt, and a 100-watt bulb, each one will have a different voltage drop because of the fact that each one wants a different current, because the power, the wattage of the bulb is related to the voltage versus the current. We'll cover that in a little bit. I want to get too far ahead. On the other hand, we wire houses like this, and you'll notice that each one of these bulbs is tied directly to the battery on the positive and negative side of battery. So whatever the battery voltage is there, it's here, it's here. Every one of these points in a circuit is referred to as a node. It's a point where current's going in and going out. There's a law called Kirchhoff's law you won't need for this class, but it's a little heads up. Kirchhoff's law says that the total current of a node is equal, or of a circuit is equal to the sum of the nodes. So this current and this current and this current are their own separate currents, their own circuit. So if this bulb blows out, goes open, it doesn't affect this, doesn't affect that, because they're not sharing the same current. Now, if you dead short this bulb, it cuts out the battery and it will shut all these out. On the other hand, up here in the series circuit, if you dead shorted one of these bulbs, the other two would just get brighter. Maybe go pop and pop out if you lost enough of them. So, and in fact, eventually the Christmas tree light things started putting in bulbs that when they failed, they shorted out. And once they shorted out, the whole set got just a tinge brighter. But if you lost enough of them, the whole set burnt out. Okay. Well, I'm going to have a little fun here for y'all. I'm going to share something again. I'm going to share an image. Is that it? No, that's not it. Yeah, that's the image I want. Tell you what, guys, hang on. That's the image I want, but not the way I want to share it. I know I have it opened up. Let me see. Yep, I've got it opened up. So let me try sharing again. Share screen. There it is. This is a nifty little graphic I'm going to share with you. And it's easy to understand the relationship between voltage, resistance, and current looking at this cute little graphic. If voltage is the push, shoving the current through the conductor, resistance is the work being done to slow it through. So it's kind of a nifty graphic. It helps understand that this relationship of voltage voltage, current flow, and resistance is referred to as Ohm's law. I'm going to go back to the book. So we'll stop this share screen. I got to get used to the technology. So much easier in the days of overhead projectors. So here we go. So I've already told you that we measure current through a circuit. We measure it with a device called an amp meter. I didn't tell you that. We measure voltage across a circuit, and we measure it with a device called a voltage meter. The symbol for voltage is an E because it stands for electromotive or electromagnetic force. The symbol for current is I. You want me to tell you why? It's too complicated to go through. Has to do with physics. Just trust me. Current is represented as an I. And resistance, somebody finally decided to use something that makes sense. They use an R for resistance. So in Ohm's law, E, electromagnetic force, is equal to the current flow times the resistance. All right, I want to get back to here. But electricity doesn't necessarily have to flow as a solid on state flowing around in a loop. Doesn't even have to flow around in a loop in one direction. It can flow in one direction, then come back in the other direction, then go forward, then go back. And it can do this in intervals. It can go on or off. It can go on fast and slowly taper off. This chart right here, which is in your book 3.1, if we look at the beginning of it, this signal is a DC signal. Normally, a DC signal would have some peak level and be a straight line represented on a chart. But in this case, this signal goes on for a little while, drops off, stays off for a while, slow and rapidly comes up, but not straight up to its peak again. Now it kind of tails off the peak. Now it goes across, comes up, and it's on, and then it's off. We call these shapes waveforms. This one is a DC waveform because this wave never, or power never goes below zero. It always flows in one direction. It's a matter of whether it's on or off. And they actually have names for the various waveforms. If you had a bunch of forms that looked like this, it would be referred to as a sawtooth wave because it kind of looks like a wood saw tooth. And this we would refer to as a square wave. But when a signal goes positive, and then as it goes up to positive, it slowly increases, then equally decreases back down. When it gets to negative, it passes below negative, and the electrons flow the other direction. So they're going forward, starting here, going forward. Now they're coming down, they get to a point, and they stop and they turn around, they go back the other way. They stop and they go forward. They get to the highest level and they you know they don't physically slow down, but the current reduces. You get less and less energy till there's zero. Or if you can look at it this way, you've got a potential voltage reaches a peak voltage, then the voltage lowers down, less poke. Well, if there's no voltage, right, there should be no current. At some point in time, I'm going to have to tell you that's not always the case. We'll get into that in the future. But for simple circuits, this is the case. This is referred to as alternating current. This is an alternating waveform, and all radio waves are alternating current waveforms. It's the principles under which radio works. And it's important to understand that waveforms like this is a sinusoidal wave or a sine wave, meaning it ramps up at an equal rate, ramps back down, and so on. I can explain to you something if I give you a little drawing, and it might make this easier to understand. But I can't really show you a physical drawing, so I'll have to create one for you. And this was a drawing I didn't use, so I'm going to come back. I'll use that, I'll clear it out, and we'll use it. Oh, it doesn't show up on my things. All right, let me do it this way. I don't want to go to whiteboard. Where did that drawing go? I'm going to minimize that drawing. We'll go back here, and I'm going to try to share again. There we go. I got a pea soup drawing I'm going to show you. And I don't need that pea soup drawing, so I'm just going to take the liberty of saying goodbye to it. All right. And I'm going to draw a circle for you. I want you guys to imagine a wheel. We have a nice wheel, beautiful hubcap, happens to be yellow. And if in this wheel, right here, right here, right in this wheel. Let's go so far as to put a center to the hub of this wheel. Hopefully I can get it somewhere close to center. If we look at this spot on the wheel, and if we spin the wheel, and I don't know how I can draw it, so you're going to have to play a little imagine with me. But if we're turning the wheel this way, as the wheel spins, it goes around like this. It will eventually come back to this spot. But now, if you put this wheel and it's rolling down the street, and you put a sheet of paper in front of it, why, if this was a pen sticking out from this spot, on that piece of paper, it would start at the bottom. It would start, look like it was going up. It would reach the top point right here. And then it would come down to the bottom. And that's what generates a sine wave. AC electricity is generally made in a generator or an alternator. The motion of magnets pull electrons through wires. And the motion, this rotary motion, creates the sine wave. Now, so if you remember that, if you keep the concept that you're dealing with a point, creating a motion, and in the case of a generator or an alternator, the magnets are lined up north and south. A north magnet here, a south magnet there, and the generator is bringing that field or that coil around and around past it. As it gets closer to the North Pole, it might make a positive flow. As it gets closer to the negative pole, it might make a negative flow. So if we had that, if I did a little drawing of the magnets, that shouldn't be so hard to do. So if we had a magnet here, I didn't want to draw that one. All right. Here we go. We had a magnet here, and we only had uh, one rotation by the magnet, it'd always be positive. That's what a generator does. An alternator does the same thing, except that it has two magnets. And or more. Actually, there are many. Depends on the but this one is got north facing down. This one has south facing up. So when the point goes by here, it's the strongest magnetic field, the strongest electromagnetic force. As it moves away, it gets weaker and weaker and weaker, and it gets closer and closer at this midpoint right here. It's equally away from two equal forces. There's no magnetic force differential. There's no potential difference. The voltage is zero. As it goes up, the voltage starts climbing as it's closer and closer to this magnetic end, but it's the opposite polarity of the one here. So it rises up. And that is how sine waves and waveforms are generated naturally. Originally, this was the only way they knew how to make electromagnetic waves. And even early radios used a device called a magneto, which was basically a generator attached to a motor, electric motor, or a gasoline engine, or anything that would rotate. And they actually made radio waves this way. I'm not going to go into it all right now, but it actually was done, and scary and dangerously done. So let's go back to the book for a minute. So electricity can be a straight DC line voltage. It can be an on off, either straight on and off, or ramped up or ramped down voltage and DC voltage. It can even be half of this or just a bunch of loops on the positive side, which are slowly going up to a peak, down to zero, back up to the peak, down to zero, and not go through the bottom. Those are DC waveforms. Or it can be what we have here, which is an AC waveform, which actually passes all the way to peaks on both positive and negative direction. And in sense, in fact, in an AC circuit, the current goes one direction, then it goes the other. The rate at which it goes back and forth between positive to negative is the frequency. We measure frequency in a unit called hertz. Remember that? We're not going to go into it in detail yet, but we will later on. It is critical to electricity. It is ultra critical to radio theory. It's what makes the whole thing work in a lot of ways, and I'll explain that as we go along. But for now, understand that difference between AC and DC is, while we usually think of DC as always being on and always being off, it can in fact be on and off at various intervals, and it can have frequency if it does. An AC wave, though, will always have some frequency. The chosen frequency in North America for electrical current and the plug is 60 hertz. 60 times a second, the wave goes from positive to negative and back up. Actually goes from zero by definition through negative or through zero to negative maximum and then back to zero again. That's one wave. And 60 of those a second is what our AC wave generates out at. Our ham radio frequencies, though, they are measured in hertz, but they're oftentimes in kilohertz, which is 1,000 hertz, or megahertz, which is 1,000,000 hertz. So 1,000,000 times a second goes back and forth, and even higher. I'm going to start to share screen. And this is the screen I'm going to share with y'all. This is, there's a similar screen in your book. Couldn't find it, so I grabbed this one. And this is the unit of measure screen. Now, I didn't circle these things, or I'd circle different ones. This was just a copy I had. And right here in the middle, in the metric system, is where you put your base unit. This one's set up for meters, but if we were talking in volts, well, the base unit would be volts. 1,000 volts would be a kilovolt. 1,000,000 volts would be a megavolt. And if you get to a teravolt, don't get anywhere close to it. I've never seen a teravolt anything, but the super collider in Europe uses many teravolts of electricity to fire itself up. That would be pretty scary. It's well above the voltage generated for power to feed nations. Anyway, so what we want to learn is kilo, mega, and giga. 1,000, million, and billion. And we also want to know, for our purposes, we're going to need to know milli, which is 1,000th of So if we had a millivolt, it'd be 1,000th of a volt. We need to know micro, which is a millionth of a volt. Everyone we're going to do is 1,000 apart. Nano is 1,000th of that. Pico, again, 1,000th of that. And we will be using in some parts of electricity measurements in picos and measurements as high as gigas. You won't use a lot of tera, but the computer world has reached a point where people are storing stuff on hard drives that are terabyte drives. You need to know these for the purposes of things like, well, our frequencies, radio frequencies are in the kilo, from the kilohertz through to the gigahertz, our frequencies. There are some radio frequencies even further above that we do for experimental purposes have access to as hams, but primarily we'll need to know kilo and mega for frequencies, for RF frequencies. Audio frequencies, which I'll cover later on, are a lot lower. And we have components like resistors that might be a kilo ohm, it might be 1,000 kilo ohms, which is a mega ohm, and which is a million ohms, or it might be a giga ohm. Very little current travels through them when they're way up there in value. That's their whole purpose, is to block off or slow the flow of electrons or current. Not the actual speed of the electrons, that's constant, but how much is flowing through the wire in terms of energy. And the other side of the picture, we have electrical devices. The unit of measure, for example, a farad, which is a unit of measure for a capacitor. A farad, 1 farad capacitor would be about the size of, about double wide, 55-gallon drum, about 6 feet high. They don't fit real well inside of radios. We use microfarad, nanofarad, and picofarad capacitors, and so on. So, in your book, find this chart, pay good attention to it. If you want to screen save this, screen save it, and or Google metric conversion chart and find something like it. But it's pretty easy to do, pretty easy to find. I'm going to stop the share on this. And I'm going to cover two things real quickly. We're going to need to know in detail in the future. Okay, I'm going to do another share screen. And I have a couple drawings. I have a drawing I want to show you. There we go. And in your book, in this chapter, there's quite a bit of discussion or a bit of coverage on various symbols. I want to point out two in particular, and I drew these up as crudely as I could. I'm sorry. The symbol for a capacitor is two plates separated from each other. It's because basically that's what a pure capacitor is. Early capacitors were called Leyden jars. They were made by putting foil in the jar and having like paper in between two layers of foil. And they were two plates separated from each other. When electrons are introduced on this side, electrons are drawn away from that side, it becomes charged up. When current flows through this, okay, well, if this is already charged, and if this was already negative and this was already positive, well, then current can go right straight across real easy. But if this is positive charge on this side, negative on that side, when current first hits it, First, it's got to move all these electrons before it can move any from the other side. So what capacitors do is they can introduce delay or pause because they take time to charge up. If we have a capacitor that's not charged, before current can flow across it, charge has to build up on both sides, positive side and the negative side, or vice versa, whichever is which. In AC current, when the current's going one way, it charges up. When the current reverses and going the other way, it opposes momentarily the flow. And we're going to discuss that in the future. I don't want to get too far ahead on this. Now, the next thing I want you to understand, this is a symbol. It's better loop drawing than this normally, but I don't have CAD here on this machine. So it's usually a symbol. It looks similar to this, a bunch of loops. And we call this device an inductor. Again, as we go through this class, why it's called an inductor will be more and more obvious. An inductor is principally a coil of wire that could be wrapped around a material to increase the magnetic field it makes. But when you make a loop of wire, you're making magnetic fields that are wrapping around each other. And they tend to oppose the charge or flow of electricity momentarily. We're going to discuss in the future how that works, but the unit measure for for inductors is Henrys. Coils, inductors, same thing. The unit measure for capacitors are farads. You will find capacitors in very, very tiny microfarad and picofarad, nanofarad measurements. And they pack a wallop at those values still. You will find inductors in very, very small values too. So I want you to get familiar now because we're going to be discussing that in further detail further in the class. So let me unshare this. Stop for a minute and see if you guys have any questions while I'm sharing the book again. Anybody get lost in any of this? Okay. Now, when we have an electrical current, an electrical flow, when the electricity is flowing, it doesn't matter what it's flowing through. As the electrons move, they generate a magnetic field at right angles to them. It might be tiny, but it's there. Electricity cannot exist, electrical current cannot exist without a magnetic field. I'm sure you guys remember in school, in grade school, learning about magnets having a north and south side. The north side of a magnet, if it hung from a string, will point to the magnetic north of the Earth and vice versa. The reason the Earth has a magnetic field is deep in its core is liquid metal, iron. And it's so hot that it's almost a plasma state. Its electrons have been literally stripped of it to some degree. And so those electrons are in constant motion. Because the Earth is spinning, you have these electrons pushed or to one side, so to speak. And so you end up with a magnetic center core because of moving electrons. About once every 50,000 years, the North Pole and South Pole switch because the mass of the material physically moves. It spins around in there. And the physics behind that is not important. What you need to know is that there's the north side of a magnet is defined north because it will point north. That should tell you that the north pole of the world is actually a south magnet, and the south pole of the world is actually a north magnet, because magnets will attract opposite charges and repulse the other, or commons. When we make an electric current flow, we make a magnetic field that rotates around the wire at 90 degrees as long as the current is flowing. Sometime through our circuits or discussions, we're going to deal with AC currents. And an AC current is going to hit a magnetic field. And when it does, it actually doesn't even need to hit a magnetic field. As a current is flowing, an AC current, it's creating a magnetic field in one orientation. When it flips directions, it now wants to make a current go in the other way, but the electrons are still in motion. They have to catch up with that. We'll discuss that in the future. These are parts of the things that make radio waves happen, make them work. So I have to introduce to you these basic principles of electricity, why it's an electromagnetic force, why we have to have some of these definitions the way we do, so we can understand them further in the future. Always remember, in electrical currents, there's always a magnetic component. Radio waves are both electrical and magnetic waves. There's an electrical wave and a magnetic wave generated at the same time. The part that goes out from point A to point B, we define it as being both, but it is actually the magnetic element which makes it work. And we'll discuss how that happens. That's why it's so important. It's critical. Now, in addition to that, there's some things you should know. An insulator is what opposes, or device that opposes electricity. But an insulator, like a light switch or something, doesn't really stop it, block it in any way. All it does is it hangs there as a point that the electricity can't get past. In a way, it's a window shade. If you have a bright light on one side of the window shade, it's bright on that side, even if you can't see it on the other side. So a switch might open up. If we put a switch in this circuit, tell you what, let me share that. Let's go back to the drawing that I did because I can interrupt it. Where is that drawing? Yeah, we'll go. Yeah, that's not going to work. All right, we'll just stay with this. You can visualize this, I think. Okay. If we put a switch in this circuit, the voltage is still here. The current has stopped flowing. Now, obviously, if you touch both sides, you'll find out the voltage is still there because the current will go through you. And if the voltage is high enough, that's not a friendly experience. But what a insulator or a switch does is it provides a curtain, a point where the charges are built up and can go no further. They don't prevent or end the current. Well, they end the flow, they end the current, but they don't eliminate the charge. Fortunately, because it can't flow, the charge can't go through you. This really, really, really is going to come and play in radio electronics, because there are times when you're going to think like a DC circuit and that the electricity stops at the switch and the switch is stopping everything. But in fact, what looks like an open circuit will allow radio waves just travel right through. If it didn't work that way, radio waves couldn't travel through the air. So when we start discussing radio waves, how they're generated, what that means and how they work, and we're actually going to start that next class. These are things that you're going to have to kind of wrap your head around, and it becomes more obvious the more I explain this. All right, I'm where I need to be for tonight. I'm going to stop for questions. Anybody have any questions? No questions whatsoever? Come on, guys. I'm not that good. Okay. Continue with chapter 3 for this week. And we will be moving forward. I will have more laughs and graphs to go through. And this is a good place to break in the class. It's going to get a little easier, but there is one thing I do. Let me reshare something. I want you guys to really study up in your book. I want you to uh, get familiar with the units of measure like I talked about. But I also want you to pay attention towards the back of this chapter. Everything in this chapter we're going to cover, but because we're going to go through all this stuff, that's I'm just kind of flipping through real quick right now, including components and basic circuits and so on. But in the back of this chapter, oh come on, it's here somewhere. There it is a symbol chart. There we go. This is not all of the electrical symbols, but this is a symbol for a resistor. Whenever you have something with an arrow through it or an arrow pointing at it, that is the symbol for that device being variable. So this is a variable resistor in two different types. We'll talk about it next week, next class, I mean. This is a symbol for capacitors. Sometimes they draw it with a curved line or straight lines. We'll talk more about that next week. And if it has an arrow through it, it means it's variable. This is a symbol for an inductor, again, variable. And I'll cover all these with you throughout the class, but I want you guys to get yourself very familiar with circuit components so we more easily understand them when we start talking about them. And it will make things a little easier.